In this section, we're going to cover more on functions and their graphs. We're going to look at increasing and decreasing functions. We're going to look at their symmetry, how to determine symmetry. We're going to talk about relative maxima, relative minima. So brace yourselves. This is a loaded little section, and here we go. So once again, we're covering section 2.2. Maybe I'll switch the page. More on functions, all about functions and their graphs. So the first thing we're going to start to look at is the concept of what is an increasing function versus a decreasing function versus a constant. Okay, and so let's look at a very simple diagram. I'm just going to go ahead and I'm going to create my own for you to follow. So if you're looking at a function, okay, so let's say this function goes like this, and this, and then at this point, let's call this point where x is 3, it does this. And let's pretend that's a perfect straight line going that way. Let's go with this point being y is 3 as well. And so the question would begin with, where is this function increasing, or is, in this case, where is it increasing? So it's increasing as you look at it. It's going left to right. Notice that I said left to right, because that's how we read the functions. So starting from the bottom up, left to right, it's going up in that direction. It's also increasing here, starting from this, about this point here, up to that point. So it's increasing at two locations. Whenever we discuss the actual value of where a function is increasing, so this is coming from negative infinity, let's hypothetically estimate this to be where x is 2. So we would say this function is increasing from negative infinity to negative 2. When I look at this function here, let's say hypothetically this is the point 1 where x is 1. Notice that I'm not even bothering with the y. And I said to you that at this point, this would be an estimate of 0.3. So we would say this is increasing from 1 to 3, inclusive for the 3 in this case. It actually would be inclusive for the 2, negative 2 in this case also. We could also argue, depending on the structure of how this is located, if this were an open dot, obviously that would not be inclusive. But let's go with closed dot for the sake of this example. Notice that these are both inclusive. Notice that I'm referring to the domain of the function when I talk about its behavior in terms of increasing, decreasing, and constant. We do not worry about the y. We worry about the y when we talk about range. By definition, what I want you to understand is when you look at the definition of what an increasing function is, we say that f of x1 is less than f of x2. Let me show you that in a different notation with a different diagram. We're still looking at a coordinate plane, excuse me. And in this case, they're starting with an open circle and they're going up as such and ending here with an open circle. What they're getting at is that we focus on f of x2. So for example, let's select 2 points. Let's select this point here and this point here. When I compare these, let's say this is technically x1 and this will be x2. notice that I'm now going to refer to f of x2 and f of x1 for that value. So what they're getting at in the definition is that the value of f of x1 is less than the value of f of x2. So if you notice, obviously this is taller than the f of x1. So that's how they define this particular definition. They also say that if you have x1, x1 is going to be less than x2. That's kind of like a duh moment, right? Now, when we look at decreasing functions, in decreasing functions, again, back to a coordinate system. All right, and so in this case, let's say I'm looking at a diagram that starts here and does this behavior. By definition, what this is saying is actually the opposite of the previous one. This is saying that f of x1 is actually going to be greater than f of x2. All right, so let's look at that. So let's say hypothetically this is my x1 and my x2 is over here. So this is x1 and this is hypothetically x2. Obviously x1 in this case is going to be considered a higher value for f of x1. So f of x1 is actually taller than, in this case, f of x2. F of x2 is actually a lower value. And that's how we define decreasing. Whenever we define a constant, we basically state that f of x1 is equal to f of x2. That's kind of a no-brainer. This would be our constant simulation here. And let's select any point. So I'll go over here and I'll select an x1 and I'll select an x2 over here. The value for the f of x1 and f of x2 will be identical. That's what they're getting at. So f of x1 is equal to f of x2. That's what they're stating, basically. Okay, so that's increasing, decreasing functions. So guess what example 1 is about? In example 1, they're basically going to give you a function. So they're going to go ahead, they're going to draw a coordinate plane for you. And then they give you a figure that does this behavior, basically. They do tell you that this particular point is where x is 2 and y is 4. They do tell you that this is 0, 0, so that's important. They do also tell you that the function itself that's being graphed is f of x is equal to 3x squared minus x cubed. Which, by the way, to start cross-teaching, understand that this is a 2, that's an even, that's an odd exponent. Because they're mixed, this is considered a neither odd or even. Okay. So behavior-wise, they want to know in this question stem to state the intervals on which this function is increasing, decreasing, and or constant, if anything. So right off the bat, I will tell you there are no constant values. So there's nothing to report there. Let's talk about decreasing. Now remember what I said to you. We're talking about the domain, and we're also looking at behavior of the function left to right. Okay, so the function is decreasing at which interval in this case? So if I look at this is coming from infinity, I can also say that this is the function here is decreasing, going in this direction. So remember, we're talking about domain, so it's coming from negative infinity on the domain, because remember, negative infinity is sitting over here, and it's coming down towards 0. So our function is decreasing at that point, based on the fact that they marked this 2 on purpose. So from this point here, I'm also going to say that this function is decreasing. So I'm going to say end from the 2 all the way to infinity, positive infinity. Remember, we're focusing not on the range. We're focusing on the domain. A lot of students, year after year, always get confused whenever we talk about increasing, decreasing, and constant, because they're thinking range. No, no, no. Always domain only, x only. Now this function is increasing from 0 up to 2. So when we talk about increasing, as to where is the function increasing, again, I'm focusing on the x values only. Think x values. Again, I'm increasing left to right from x is 0 to x is 2. Notice that I keep saying x, x, x. It's all about x. Okay. Same question, STEM, example 2. In example 2, or actually example 1, part 2. So this is example 1, part B. We have another coordinate plane. I have a constant sitting at y is 2, and it's pointing in this direction. I also have an open origin point, and a line increasing to positive infinity going that way. So let's answer this question. Let's start with a constant, since we haven't had a constant yet. Now, they did not give us a function. We don't know anything about the function. So what we see is the constant is from negative infinity to 0. Negative infinity to 0. Remember, this is where x is 0. When it comes to decreasing, this function is not decreasing at any point. It is, however, increasing. If I look at the graph, I can see clearly that it's starting from 0 all the way to positive infinity. Notice that even though it's not inclusive, I am using a parentheses. That's why it's not inclusive. Okay, and that answers my question 1. Now, what do we consider a relative maxima and minima? They call it maxima. And the other question is relative minima. So relative maxima, imagine, if you would, again, a coordinate plane. And let's say hypothetically I've got a diagram that is doing this loop-de-loop behavior as such. This is considered the point A, where x is A and y is f of A. Let's call this point down here B, where x is B, technically negative B, and this y point would be f of B, whatever that value would be. So what we say in this case, it's a relative maxima, if f of a is greater than all values for f of x. And obviously that indicates that the a value is greater than any other value. In a relative minima, it would be the opposite, because this would be the lowest value, so that lowest value would always be less than any other value for f of x. So relative maxima, relative minima. This is the relative minima, and that's an example of relative maxima. The highest and the lowest point of a graph, basically. And that's just notes. They don't really go into an example there. Now, we're going to next talk about, and by the way, this concept you're going to see quite a bit in calculus. When you get to calculus 1, one of the first things you're going to talk about is differentiation. And when we use differentiation, you're looking for relative minimum and relative max for a particular diagram. Right. So anyway, that's just informational. The next concept and question that we're going to talk about is the test for symmetry. There are 3 tests for symmetry, so no matter which question I go over with you right now at this point, I need you to understand that you're going to look at the question and attempt 3 different tests. So we're going to start with y-axis symmetry. That's test number 1. So take your paper and let's split it into 3 little columns. This second symmetry is x-axis symmetry. We will test for that. And the third one is origin symmetry. All of these are the 3 tests for symmetry that you will do for a typical graph given a function of some sort or equation. Okay. What I need you to understand is when I'm testing for x-axis symmetry, I make the x its opposite sign. If it happens to be positive, I'll use a negative. If it's negative, I'll use a positive. When I test x-axis symmetry, I'm going to take the y and I'm going to make it the opposite sign of whatever it is. When I test for origin symmetry, we're going to test both. And we're going to do that by using a negative x and a negative y, or basically the opposite sign of whatever it happens to be in the equation. If once you substitute in that opposite sign for the opposite variable of relative to the symmetry you're testing, if you obtain the same result, then it is symmetric with respect to that axis. But if your result is something different, then it is not. So this is going to be example 2. And this is called test for symmetry. So watch. The question in this case says, determine whether the graph of x equals y squared minus 1 is symmetric with respect to the y-axis, the x-axis, or the origin. So we're going to take our equation. I'm going to write it down across all 3. So you see where I'm starting. Okay, and now we're going to apply our test. So I'm going to test for y first. So that means that since x is positive, I'm going to use negative x is equal to y squared minus 1. And come over here, do the same thing. Actually, no, sorry. For the x-axis, I'm going to do the same thing with respect to the negative y. So x equals negative y squared minus 1. And for the third one, we test both. So this will be negative x is equal to negative y squared minus 1. So if you notice, the key is if it's y-axis symmetry, I'm plugging in a negative x. If it's x-axis symmetry I'm testing, then I'm substituting in a negative y. If it's both, then I'm doing both with their opposite signs. Now, what happens here is that I'm going to end up with negative x equals y squared minus 1. And we never like a leading variable that's negative, so I'll have to multiply by negative 1 across to get x is equal to negative y squared plus 1. Not the same, so this does not have y-axis symmetry. I will repeat this over here, where x is equal to negative y squared. Well, that gives me y squared minus 1. That is identical, same. So this definitely has x-axis symmetry. This is a winner chicken dinner. Okay, now what happens in the second one is I end up with negative x is equal to y squared minus 1. Again, we don't like a negative variable leading, so we'll multiply by negative 1 to get x is equal to negative y squared plus 1. Not the same. So therefore, this also is a no origin symmetry. And that's a key to this particular example. Another practice of this would simply be example 3. So I'm just going to go ahead and go to example 3. We're testing for symmetry. The question says, determine whether the graph of y equals x cubed is symmetric with respect to the y-axis, the x-axis, or the origin. So again, we create our little grid for y-axis, x-axis, and origin symmetry. And if I apply the test that I stated earlier, this will be, in this case, y equals negative x to the third power, which is going to yield me y equals negative x cubed. So this is a graph that is not symmetric with respect to the x-axis, because this ends up yielding me where y equals negative x cubed, and negative x cubed is not the same. Not the same. For x-axis symmetry, I'm going to substitute in negative y. For this one, we use negative x. So we're going to have negative y is equal to x cubed, which we do not like to have a negative leading. So we'll multiply by negative 1 to get y equals negative x cubed. Again, it does not line up as the same function. So in this case, this is also not symmetric with respect to the x-axis. So now we apply the origin. In the origin, we do both the x and the y values with their opposite. Remember, I happen to be using negative because I'm assuming the variables are positive initially, which they are. So in our case, we're going to have negative y is equal to negative x to the third power. Initially, you're going to get negative y is equal to negative of x cubed. And then lastly, we're going to multiply by negative 1 to get positive y is equal to x cubed. Notice that this is the same as the original function, and therefore this is a winner. This does have origin symmetry. As a matter of fact, all cubic functions have origin symmetry. Now, if you look at the equation of a circle, the circle is the only equation that has all three. So any equation that is a circle has all three symmetries. If you wish to check one out, I can give you an easy one to try. So let's say I give you x squared plus y squared equals 25, and you can go ahead and test all three symmetries. You do that on your own time. This is a summer term, and I cannot tell you that I am concerned about time. All right, the next concept is even and odd, and I'm going to give you the skinny on this one. Even and odd functions, the easiest way to do this, how to determine if a function is even or odd. Now there's a graphical method, and there's also the simply look at the exponents. Now look, you know it's even if f of negative x is going to be equal to f of x. And you'll know it's odd if f of negative x yields you the negative of f of x. I could give you a quick visual for an even function. A parabola is a typical even function. So if I show you a parabola, that is exactly what that is, an even function. It's also a square, right? Y equals x squared, even exponent. So that's another way you could tell if it's even or odd. Now, an odd function typically will have origin symmetry, as we just discussed. And if I have a function that's going through here as such, let's say hypothetically I have this function, this would be a perfect example of origin symmetry or odd. If I drew a perfect cube function, which this is not, let's do cubic function where y equals x cubed. Again, notice that that is an odd exponent, so again, that is the hint or the big picture. You can also tell based on the diagram itself. So in example 4, what they do is they give you 3 little drawings. So I'm going to draw them here with 3 little coordinates. Okay, so the first one is cubic or origin symmetry. See how it's going, and it's producing this diagram where you can tell that these are opposite of each other. The second one is even. It literally looks identical. So this is an example of even. This again is an example of odd. And then you have the neither. And the neither, you just have some random parabola on one side of the graph. What I want you to notice here is that over here on this point, let me use a purple marker. So if I have negative x, this is equivalent to the value of negative of f of x. And if I look at this graph over here, or this part of the graph, I have positive x and f of x. That's one of the ways you know it's odd. You know it's even if, like in this case, I have negative x, but the y is still f of x. And over here you have a positive x, and this is f of x. This is just x f of x. It's neither odd or even, or odd and even, or... Alright. Now, by exponents, which is the easiest way, is example 5. In example 5, we're going to identify if it's even, odd, or neither. So if I say to you in the first example, they say, hey, I have f of x is equal to x cubed minus 6x. Well, that's 6x to the 1 power. odd, even, or neither. Both of these, and I'm focusing on the exponents, that's an odd number, so is that. Guess what? This is an odd. In part B, if I give you g of x is equal to x to the fourth minus 2x squared, what do you notice about these exponents? They're both what? Even numbers. So guess what? This is an even one. In part C, I'm going to give you one where I have, let's say I have h of x is equal to x to the fifth power plus 3x squared. You see how we have mixed values here? This is a odd. This is a even. So because it's mixed exponents means it's neither odd nor even. Example 6. Now you guys have done this chapter in algebra. I want you to remember that. So, by the way, if you want to do this the excruciating long way, let me go back for a minute on example 5 because I'm sure you're going to hear. So, say hypothetically that I do f of negative x. Substituting in negative x is the way to go to prove this. If I have negative x to the third power minus 6 times negative x, that is how I can prove that this is going to be an odd function. If you remember, if I substitute a negative x and I get the negative of f of x, notice that this is going to give me negative x cubed plus 6x, which in essence is the equivalent of the negative of x cubed minus 6x. Hence the negative of f of x. That's how you know it's odd, or that's how you prove it. And if I were to do the same thing with part B, you'll see that in part B, if I do g of negative x, this is equivalent to the same function because negative x to the fourth minus 2 times negative x to the second is going to yield me the same function. It's going to yield me, in this case, x to the fourth minus 2x to the second. It's the same function. That's how you know this is even. The long way. Now, if I did the third one, what happens is you get a mismatch of values. Because if I do h of negative x, well, this is going to give me negative x to the fifth power plus 3 times negative x to the second power. So I'm going to get negative x to the fifth plus 3x squared. So you notice it's a mismatch. This is not exactly match the equation. This does. So that's how you know it's neither. Neither odd nor even. I just want to make sure I covered that real quick. Now, in example 6, we talk about piecewise functions. This one also tends to be a hotspot for students because you forget how to analyze things and you have to start with the inequalities themselves. So, in piecewise functions, what I want you to remember is that, in a typical example, you actually have probably experienced this, is your phone bill. Because usually they give you introductory offers. Those are piecewise. For a specific amount of time, you pay X dollars. So in this example, they're telling you, look, you're going to get a phone plan. You're going to pay $20 if your minutes used are between 0 and 60. That is inclusive. Notice the equal to sign. So between 0 and 60 inclusive. And once you go past your 60 minutes, we're going to charge you 40 cents. So this will be 20 plus 40 cents times t minus 60. And that will be the case if t is greater than 60. So you're at 61 minutes, 62 minutes, 70 minutes, and so on. So understand that in this question, they're going to ask you for specific values. So what if you use 30 seconds? Well, if I use time 30 seconds, 30 is between 0 and 60, so I'm simply going to pay 20. In part B, they're asking you, what if you use 100 minutes? Well, if I use 100 minutes, that means that I'm definitely 40 minutes over my 60. So we're going to employ the formula where this is 20 plus 0.40 times 100 minus 60, hence the 40. So 40 times 0.4 at 20, you'll have your total bill, which I believe should be $36. Remember, this is 16 because this gives you 40, and 40 times 0.40 is 16. And then 16 plus 20 gives you 36. And that is the same thing you're going to do in example 7, which I'm actually not even going to cover because the concept is pretty much what it is. You also have to understand stepwise functions. They're not going to test you on it, but they might give you a homework question on it. And stepwise functions, you're going to use technology, which is why we don't really get into it. You're going to use the int function, which if you want to see me for tutoring, I will go over it with you happily. But I want to cover what's covered for you and what's important to you. So we hop over to the difference quotient. And understand the difference quotient is another concept that eventually you're going to use in calculus. So in the difference quotient, we're giving a function f of x plus h minus f of x and all of this over h. They always give you the f of x. You have to solve for f of x plus h. So if I say to you an example 8, we're going to evaluate and use the difference quotient to simplify the expression where f of x is equal to 2x squared minus x plus 3. So once again, understand that they're already going to give you the f of x. We have f of x. What I need is f of x plus h. So that means that everywhere I see an x squared and an x in this example, I'm actually going to input x plus h. So this becomes 2 parentheses x plus h squared minus x plus h plus 3. So what's going to happen is you have to FOIL this part. So this is where students always forget. So you have 2 parentheses. This becomes x squared plus 2xh plus h squared. And then obviously you can go ahead and distribute your negative if you watch. So you get negative x minus h and then plus 3 because you're distributing this here and here. You also need to distribute the 2 to all 3 terms. You're going to end up with 2x squared plus 4xh plus 2h squared minus x minus h plus 3. Now all of this has just simply gotten you through the first part of the formula. We now need to subtract f of x, which is the 2x squared minus x plus 3. And remember, all of this is over h. So once I distribute this negative, I'm going to end up with 2x squared plus 4xh plus 2h squared minus x minus h plus 3 minus 2x squared plus x minus 3. And again, all of that is over h. Now I want you to notice this cancels with this. X, negative x, is going to cancel with positive x. Positive 3 cancels with negative 3. That goes away. What you're left with now is simply 4xh plus 2h squared minus h, all of this over h. Technically, at this point, I can simply take out h, which is common to all three terms, in the numerator to get 4x, so h parentheses 4x plus 2h minus 1, and all of this over h, and what will happen is the h's will cancel. And your final answer in this case should be 4x plus 2h minus 1. Now keep in mind that in calculus, this will have to do with limits, and eventually the notation that they're going to give you will be as h approaches 0. And then since h is approaching 0, all terms are going to disappear. And you're going to eventually be left with 4x minus 1. Now, notice what I just said, and I'm going to show you real quick how to do the derivative, which is one of the first things you're going to learn in calculus. That is your first derivative. That is what happens when this term, when that h approaches 0. That's going to go away. Notice how I got this value. Notice that I had 2x squared. 2 times 2 is 4. Take away an exponent, you're 1. This is a constant. You had a minus x. Technically, minus x to the 1. 1 times negative 1, well, that's minus 1. If I take away 1, I'm back down to 0, which means it's a constant. This little calculus fun. Have fun.